So today we're going to talk about curvilinear motion. So curvilinear motion is simply curved motion. So it's motion where that doesn't act in a straight line. So in general, within curved motion, the velocity vector is tangent to the path and points in the direction of motion. The acceleration vector is perpendicular to the tangent of the curve and points inwards. This isn't always the case. Sometimes there can be acceleration that is tangent to the path, such as, for example, a rocket taking off horizontally. It would have acceleration from its engines and also acceleration due to gravity. So any vector can be split into x and y components in 2D motion. So these are the rectangular components of curvilinear motion. So for example, position r equals xi plus yj. Velocity is simply the first derivative of the position, which would be dx dt I plus dy dt j, etc. And acceleration, the same thing. The second derivative of position, or the first derivative of velocity. We can use regular calculus to find velocity from acceleration, velocity from displacement, etc. So using either derivatives or integrals. We can also use the path equation to find the direction of velocity, of the velocity vector rather, by taking the tangent of the path equation. Since velocity is always acting, the velocity vector will always be acting in the tangent direction to the path. We can take the tangent of the path equation to find which way the velocity vector is acting. Projectile motion is a type of curvilinear motion. So just to note, we can use the equations of constant acceleration. We know that gravity is constant. So there's no acceleration generally for projectile motion equations in the x direction. Also remember that acceleration is normal to the curve and velocity is tangential to the curve. And we can use the path equation to find the direction of the normal and tangential vectors. So for curvilinear motion, or projectile motion rather, there is a bit of a procedure. So first we should list all of the known variables. So time, Vx, Viy, Vfy, and Ay, Viy being initial velocity in the y direction and Vfy being final. So we take those and we list the ones that we know and the ones that we don't know. Then we'd like to determine the initial and final direction of velocity and acceleration. So normal and tangential, not respectively, but you get the idea. Then use the equations to solve for x and y components. So remember that the derivatives are generally taken with time, dt. Just a quick note here that if you see x or y with a dot above it, that is the first derivative of x or y with respect to time, meaning it is the x or y velocity. Same thing, two dots. X with two dots above it would be acceleration, so the second derivative of the x displacement with respect to time, which equals acceleration. I'll use that notation a bit in my solutions. Fourth and finally, present the solution either with components, so I or j, or a direction, so degrees above or below the positive x-axis is generally what is used, but you can choose your own coordinate system, choose where to measure from. So for the first example, the video example, we'll just go over a particle which travels along this path, y equals 1/2 x squared, with Vx being equal to 5. We'll just assume it's unitless for this. It could be feet per second or meters per second or any other velocity unit. So we want to find the position at time t equals 1. And then I also have another example linked in the description below for some projectile motion question, or more of a projectile motion question just based on the path. So we'll go ahead and start this example. All right. So what we want to do is we want to use the velocity in the x direction to find the displacement in the x direction at time 1 first. So that's our first sort of step to this. Since it's not projectile motion, we don't need to go through the whole thing. So we can say that Vx equals 5t. So that's our equation, or sorry, that's our velocity rather, which is equal to dx over dt. Therefore, dx equals 5 dt. And that's just rearranging that formula there. So then we want to take the integral of both sides of this. So I'm just going to move it down here. So what we're going to have is the integral of dx up to an unknown x from 0. Again, we can choose our own coordinates here. So we can say that 0 is our limit, our lower limit of integration. And then this equals 5t dt from 0 to t, our unknown time t. All right, and then we just simply do this integration. So we'll end up with x is equal to 5t squared over 2. And if we put in t equals 1, then we have the x coordinate 5, 1 squared over 2, which is simply 5 over 2. Okay, so that's the first part done. We found our x displacement. So we can then use the path equation to find the y coordinate. So, excuse me, what we'll do first of all is use the path equation. So we'll call it sy1 equals 0.5 times 5 halves, which just comes from the x here, since that's the path equation, squared, and that is equal to 3.125. So then we have our x here and our y here. So just simplify it a bit, just make it equal to y rather than sy. So then, to get our overall position, which we can call r, without any direction, all we have to do is add the square of x plus the square of y and square root it all. So x was 5 halves squared plus y, which is 3.125 squared. And this ends up to be, approximately equal to 4. So that's our final answer. And that's everything for now. Thank you again to Zoom, or not Zoom, rather, sorry, Loom and Google Keep, and of course to my professors, and to you as well. I hope this helps.